Ready to see the stream?
Not yet. Yeah, I see it now.
All right,
We're
let's
live.
do it. Hello, everyone. Welcome to today's brand new episode of Corecast. I am Tim, your host.
Mikey.
I'm Sahil. Welcome everybody to a brand new exciting episode of Corecast. Before we get started, if you haven't already, do join the Discord channel. And if you're watching on YouTube, where we do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern, do ask us questions during the episode and we'll get to them. So without further ado, let's get to it. So I guess Tim and Mikey, this is a episode I've been very much looking forward to discussing about supersymmetry. And basically, we had come to this episode by our previous episode where we talked about how quantum mechanics and symmetry are actually very much linked together. And Tim, maybe you can describe high level in a little bit. And we described like what are the possible symmetries that you can add to a theory besides like, space and time being related to each other, translational, rotational symmetry. And so this episode covers essentially that. So I guess, Tim, can you start off by describing like at a high level what we talked about in the previous episode, and then like we can segue into this one.
Yeah, in the previous episode, we emphasized the importance of symmetry. In normal physics, in high school, in college, you learn physics. You might not have learned about the concept of symmetry yet, but physics does come with it. A lot of objects that we see contain symmetry, but to some extent, it's kind of like an afterthought. Like you could use it; it will simplify things, but you don't necessarily have to use it. But when we move on to quantum physics, things get a lot trickier because in quantum physics, things are a lot more difficult, and a lot of times we actually don't have control in our equations. So it turns out that one way out of this conundrum to solve these very difficult problems is to lean on symmetries more heavily. And in fact, in modern physics, symmetries would be actually the starting point to build a physical theory. So that's why symmetry plays such an important role.
Gotcha. Did you were saying something, Mikey?
Yeah. I mean, I guess I missed last week's episode, so I'm not sure how you guys describe symmetry. But I would just add to that I guess at least in my view, the idea of symmetry is crucial for understanding anything, right? Because you're asking the question, out of this vast collection of objects that I see, are there two things that are similar, that are pretty much the same? Is there a relationship between these two things? Is there a relationship between these two things? And that's what we usually refer to as a symmetry. It's a way of organizing things in terms of their relationships with one another. If you don't have that, then I would say we don't really know how to make progress.
Yeah, and for people more interested in like why that's the case, do check out our past two episodes where we did a very in-depth dive into symmetry 101 and then symmetry as it relates to quantum mechanics. Both very fascinating episodes in my own opinion. So I guess let's jump to the crux of this episode. So Tim, I'm going to ask you this question flat out. What is the greatest possible symmetry that you can like put into a theory or into nature? And what would that be?
Yeah, I mean, there are many candidates, but I would say, and physicists have studied many theories, and many of which are way more symmetric than the world that we live in. And I would say, and this is somewhat subjective, but probably most physicists will agree that the greatest symmetry ever discovered in physics has to be supersymmetry. Like the name, I think, does do justice to what it does. So it is really a symmetry that is supercharged. By the way, pun intended. Um, it's a very powerful symmetry, and there are many unexpected discovery almost, and it just feels like it's just one of those things that when you learn it, when you realize what it does, it's got to be there. It just seems so appealing, I would say. Do you agree, Mikey?
I would say so, yeah. I would, if I had to bet money, I would say that supersymmetry has to play some role in nature.
Gotcha. Yeah, it'll be interesting to dive into this. So I guess like what would you say is like I guess your reason for, so before we describe what supersymmetry is, we're just imagine this is like more abstract thing, which is highly symmetrical in this very abstract way. And wanted to understand, like, why do you what's behind your conviction that like it exists, or like that it's reasonable to expect that it's there from like what we've talked about in past episodes? I guess, Tim, I'll point to you on this question.
Yeah, and I think this happens when seemingly unrelated things can somehow be related to one another. When that happens, it's like a breakthrough. And if you look at physics, the way symmetry plays a role, and usually they're the distinct category. For example, our audience might be familiar with Einstein's theory. Einstein's theory relates space and time. So space and time are related by a symmetry. It's called the Lorentz symmetry. There's a symmetry relating the two. And in particle physics, there are different symmetries, like positron and electron. They are antiparticles of one another. They are related, right? But these two symmetries always tend to kind of fall into these two groups. It's either how it relates to, how space and time movements versus the different types of particles. Those two things seems distinct. Like the space where particles live in versus the types of particles. They seem totally different. But if we believe space-time itself and particles that live on it are unified into one grand scheme of things, these two separate things have to merge together. And that's where supersymmetry comes in. Supersymmetry is the first step where you link space and time and the different type of particles and mix them up together. And it turns out once you assume that that's possible, you get this amazing mixture of, basically you get symmetry but elevated. That's why we call it supersymmetry.
I see. So are you saying that like basically supersymmetry in its like final form, for lack of better words, is essentially that like everything is kind of interchangeable with everything else?
Well, we're not quite there yet, but at its final form,
Okay.
that does happen. But in the beginning, if you just say, hey, let's bridge the gap between space and time and particles, what you get, it turns out, is supersymmetry. That's the first step. But of course, the ultimate form, as we will describe. At the end of the day, if you take it to the logical extreme, you get super duper supersymmetry. I don't know how else to put it.
That was a question I had in my mind. Like, what if somebody came up with super duper symmetry as like a thing that superseded supersymmetry?
Well,
anyway, Mikey, were you going to say something, or?
Oh yeah, I mean, just a few things. Yeah, so I mean, instead of saying super duper, they just say n equals 2 for 8.
Not as not up my cup of tea for naming, but I guess if you discover it, then you get the first crack at naming it. So
yeah, but I did want to go back to your original question though about like why I have this kind of conviction. Just because like I mean I remember when I was kind of going through the thought process about whether or not I wanted to like spend time thinking about this idea, and you notice like when you look at the world around us, which is we exist on macroscopic length scales. We're macroscopic beings. We see things, the universe macroscopically, and we also see it at a very cold temperature. Right now, the temperature is very, very cold relative to what the universe has been in the past. And so when we observe the universe, we see lots of variety. We don't see a lot of symmetry. Like all the different atoms we observe have different masses. Things have different colors, textures. But when we raise the temperature, when we look closer, we start to see a lot more symmetry. Like Tim mentioned, we see positrons and electrons have exactly +1, -1 charge. So there's a symmetry there. We see neutrons and protons have almost exactly the same mass. So there's an approximate symmetry there. And we notice that as we raise the temperature and as we go smaller, which are the same thing in a sense, the number of symmetries becomes more apparent and increases. And things that seem totally unrelated, we find out are actually, sisters and brothers of each other, like particles, for example. So just following that very, very consistent trend, we would expect that as we go to smaller and smaller distances and higher temperatures, we would see more and more symmetry arise. And if you just take this to the logical extreme, what is the most symmetric thing you can possibly have. It's the situation where everything is related to everything else, right? And that's
Hmm.
the kind of relationship that supersymmetry implies about a high temperature universe.
Gotcha. So actually, I want to. That's actually an interesting point you mentioned. I want to clarify one thing for the audience, just in case if the connection is not as clear. So two things I want to bring up. First one is you mentioned this connection between higher temperatures and smaller distance scales. Can you give like a one sentence kind of connection between the two?
Yeah, yeah. So this is something we talked about in the past, but it's just the simple idea that everything is made of waves. And so if you have a more intense wave with peaks and troughs very close together, that's a very energetic high temperature wave. And
Mm,
that's related to the distance spacing between the peaks and the troughs. So
mm,
close distance, small distances is related to high energy.
mm.
Yeah, I'll just leave it at that. 'Cause
Okay, and then of course higher temperature related to higher energy. So that makes sense. And then the second piece of what you were talking about is that as you increase the temperature or energy or reduce distance scale, things start to become similar to each other. Is there any experiment that confirms that for particles that we see like a proton and neutron at higher temperatures, they become basically the same thing, or like, yeah, I just want to clarify. I want to understand that more.
I guess the first example that comes to my mind is water freezing. Is water is more
Okay.
symmetric at high temperatures. Like ice has less
Mhm,
symmetry than water. So,
mhm,
and that's because when ice freezes, the molecules that used to be have a spherical symmetry. They can point in any direction. They lock up, and they all start to
mhm.
point in one direction. Um, so I think water is the simplest example of like a symmetry that exists at high temperatures that disappears when you get to low temperatures. But you see this also in particle physics. Um, the protons and neutrons there, I said there's an approximate symmetry there, but if you crack them open, you actually see that they're made of smaller particles called quarks, which fit into a much larger, nicer, neater symmetry pattern.
Yeah, and I just want to add, like, that the symmetry between protons and neutrons, you can test it out in collider experiments. If you smash protons and neutrons together, at certain energy, you see that the interaction rates are very similar, and that can be explained by the approximate symmetries that they have.
Yeah. Basically, as you increase the temperature, it becomes harder to distinguish any one thing from any other thing. Everything just mixes together
Yeah.
and is basically the
Mm.
same thing. It's like melting soup, you know?
Fair enough. Yeah, no, just interesting thing I wanted to spend a little time on. So I guess Mikey, since you've been talking about your convictions, could you maybe I guess give us a kind of I guess like historical overview of supersymmetry? Like why did it even come about? What was the need for it? Like, yeah, what problem was it solving? Even if like the way we understand today is different. So just historically, yeah, high level.
Yeah. So yeah, historically, I think this is part of the reason. So supersymmetry in the physics community does have its fair share of haters. There are people who like to hate the idea for whatever reason because of its association with something called string theory, which is
Mhm,
string theory is often touted as the most likely candidate as a theory for everything.
mhm,
And in string theory, the idea is that all of the particles we see that have different properties and different masses and charges and things like that, they can all be thought of as the same object, like a single vibrating string. Um,
mhm.
and if that's true, then it really is true that everything is related to everything else. Everything's made of the same object, the string. And so supersymmetry first arose historically in the context of string theory. It was realized that string theory required something like supersymmetry in order to exist. If everything's made up of strings, then there has to be some relationships between. Well, actually, we should back up, huh? um, I just realized we didn't really talk about exactly what supersymmetry is. And so I guess just to say it very quickly, we talk a lot about particles on the show. So hopefully the viewers are all familiar with the fact there are many different kinds of particles with many different kinds of properties, mass, charge, or whatever. But there really is one big distinction, kind of like two different types of particles. There are particles that can pass through each other, that can occupy the same space at the same time, and there are particles that can't. Um, the particles that can't are the particles that make up our bodies. We call them fermions. My hands can't pass through each other. That's not related to the fact that fermions can't occupy the same space, but it comes along with it. And supersymmetry is basically the idea that these two types of particles are actually part of a larger structure, part of like the same family, if you will. So for every time you have a particle that can't occupy the same space as another particle, there's another particle that is exactly like that, but it can. I'm not explaining that very well, but it's the idea that these two kinds of particles are basically cut from the same cloth. And this is the idea that's motivated by string theory, the idea that everything is made up of strings.
Okay. So I mean, let's talk about this. When I first learned about supersymmetry, which was quite a while back, and I'm pretty sure the conception of it has changed, which we can allude to more, is that every particle that we know today has what I was told is called a supersymmetric partner. So, and these particles have different properties, as you're mentioning, in terms of like the particles in my hand can't pass through each other, but there's like a corresponding set of particles that like could, I mean, also called like bosons and whatnot for the more familiar members of the audience. And so there's this supersymmetric partners, and then it was said that we haven't discovered these particles yet, these partners, because we haven't probed at high enough energies. So I guess Tim or Mikey, can you jump in and like tell me, is that conception of what supersymmetry is correct at that, when it was first discovered, and then what has it like morphed into? Is it the same thing, or is it just want to understand that more?
Yeah, so I would say this is technically a correct description of supersymmetry, but it's too basic. It doesn't tell you like, and the thing is, because some people only learn that fact, like, oh, every particle has a partner. Well, so what? We don't see that. So supersymmetry is bunk. It's useless. So that's why we create a lot of these superficial haters of the idea of supersymmetry. I would say once you get a little deeper into this field, the insight is incredible. So I would say supersymmetry can be elevated into the concept called superspace. The idea is that instead of thinking of space-time as up, down, left, right, front, back, and time, future and past, we actually think of space-time as that plus a supersymmetric dimension, literally like an extra abstract dimension, right? And the fact that the particles that we have are the way we feel it is because it exists in a certain dimension in this superspace. So if I were to able to walk into this superspace, let's say I take one step into this superspace, the type of particles in my hands would change. So that's a profound, much more profound realization. It's not just that every particle has a different partner. There's just one type of particle, but depending on where the particle is located in superspace, it manifests into different types of particles. So maybe, and if a particle is in superspace, one location, it's an electron, and if it's in a different location, it will be the partner of electron, which we got selectron. It's a pretty bad name. But then it tells you that, hey, the way every particle is just because of their location in this superspace. And I would say if you accept that, if you understand this idea deeper, you realize that this isn't just any vanilla. Oh, you're gonna pair up some particles like the antiparticles. No. This is way more profound. We're literally generalizing Einstein's idea of space and time into super space-time.
One question about that is like, could you explain further, like, why is that even like more symmetrical, or like why does that introduce more symmetry than like adding in more spatial dimensions, or like even more dimensions to space and time? Like, I just want to understand that more.
Yeah, because if you like this idea of supersymmetry, if you believe that it's true, it's telling you there's something about the structure of space-time, right? Like, for example, if we add more dimensions, Like let's say there's an extra dimension I can move into. Well, it's just going to be an extra dimension that I can move into. It doesn't tell me anything about space-time itself. Space-time and particles are still separate entities. Yeah. Space-time is just the places where particles can live in, right? And they're not one and the same. Supersymmetry is different because it says that the type of particles that you have is literally depending on your location in superspace. So you can literally move in superspace and change particle types. And vice versa, you can change particle types, and if you change enough times, you can move in space-time. So it's telling us that, like, look, space-time itself, even though you think of it as some kind of fabric or whatever, it gives you a hint. Maybe space-time can be broken up into these little bits. And if you're hopping between these bits of different types of particles, you're also hopping in space-time. It's like a unifying thing that unifies space and time and particles.
So I guess I want to kind of try to draw an analogy to make this more concrete. So I guess, like, what analogy would you give to, like, explain more of the significance of this, like, in the sense that, like, what would it be like to walk in this like supersymmetric direction or dimensions, as you called it?
Yeah, that's a tough one because the mathematics is very complex. It involves, like, geometric, algebraic geometry, topology, and all that. But I think this matrix analogy is pretty good.
Okay. Okay.
So imagine the universe is the matrix. Like, I don't know if our audience has seen the movie. Like, there's Neo, Agent Smith, right? Like imagine if Agent Smith were trying to go from, like, US to Europe, right? Of course he can walk in the matrix. That's a dumb way of doing it. But Agent Smith can, like, do his Agent Smith things and, like, convert, like, a pilot in Europe, like a helicopter pilot in Europe, into Agent Smith, and he has moved, basically. Like, supersymmetry is kind of like that. You can just, like, hop around between particles, and all of a sudden you have moved. It's telling you that there's something interesting about the structure of space-time. But please don't take this analogy too literally. But I don't know how else to understand it. I don't know, Mikey. Do you have better thoughts?
It's difficult to describe intuitively. I know that I wouldn't want to take a walk through superspace. That wouldn't be good for me.
Yeah, I mean,
Why wouldn't that be good for you?
Because I just turn into bosons and I fly apart.
You'll die, yeah. Well, okay. Well, supersymmetry, we know that in real world, supersymmetry at best is hidden. It's broken. It means that, like, in our universe, supersymmetry is not fully realized. Like, we talked about this in the previous episode. Like, of course, it means that maybe if you average over all the possible universes, you will have supersymmetry. But in our universe, if you walk in that direction in the superspace, oh, hell is going to break loose. Like, you do not want to feel that. Like, Tim is going to be like super Tim, but that just means that I'll become, first of all, I need so much energy to do that. And then I'll turn into some, like, really unstable particles and just decay. And I would not exist, sadly.
Yeah, remember, humans like asymmetry. If a universe is too symmetric, then structure cannot exist. So if we were going to superspace, we would be exposed to the symmetry, and our ability to maintain structure would correspondingly go away.
Oh, that's most unfortunate. Actually, this segues nicely into my next question. Is, like, why don't we see this? Like, what is preventing us, and why is that preventing us from seeing it? Like, yeah, what gives?
Before we jump into that question, I don't know, like, this might be a fringe thought, but I would argue that we do see it. Like, supersymmetry is an explanation, if you like, for why there are these two types of particles, bosons and fermions. The idea that supersymmetry might be restored at some higher temperatures, yeah, sure, we don't have any experimental evidence of that yet, but there, as Tim mentioned, it's the idea that there is another kind of dimension in space, like kind of a binary dimension, not one that you can walk through continuously, but one that you can just take one step in and one step out of. It's like a bifold type of symmetry, which is basically what supersymmetry is. And that gives you a way to describe photons and quarks in kind of a consistent language. So I don't know. For me, it's an explanation for why we have these two types of particles, even though there's no symmetry per se, like there's no partner for the photon. We don't see this extra structure. But assuming this kind of like bifold dimension gives you a way to describe these particles in the same language. So I would argue that we do see signs of it. We see the remnants of the broken supersymmetry.
Yeah, yeah. I suppose I do like that perspective, Mikey. I mean, I haven't exactly thought of it this way. Like in physics, a lot of times you could take something for granted. You'd be like, hey, look, we have different types of particles. We have particles of light, particles of forces, particles of matter. These are bosons and fermions and graviton, right? They're different. They have different spin. That's one thing. You know, I know spin is a more technical term, but the deep brute fact about supersymmetry is that it relates particles with different spins. So we could take the perspective and say, hey, look, there are just these particles with different spins. Whatever. That's just how life is. Too bad, right? Or we can say, hey, guess what? You know, there's actually only one type of particle. It's a super particle, and because of the way it's situated in our universe, it disintegrated into different types of particles. Particles of spin 2, like graviton. Particles of spin 1, particles of spin half, particles of spin 0. You can take that perspective, and if you like that perspective, then you see the universe as more beautiful, I think.
Yeah, and on top of that, like, you know, so much great insight and advancement in physics has come from asking the question, how do I take these two things that look different and view them as part of the same object? How can I view them as actually being similar, even though they look different? And whenever we ask this question, that's always what leads to the big advances in physics. And supersymmetry is like the ultimate version of that.
Interesting. Yeah, actually, one question I have about this is more a speculative question and kind of alluding to what we were talking about in our, at the beginning of this episode, is that does this mean, as Tim, you were mentioning that like, if you were to average over all universes, assuming there are multiple universes, you would see that there is like supersymmetry. Does this mean that like if you take this to its logical conclusion, that there's one mechanism that like generates all these different particles that give rise to our universe and other universes?
Yeah, possibly, and there could also be multiple mechanisms. Like, so if you believe this idea of supersymmetry, it means that supersymmetry has to be broken, just like how water has to freeze. The supersymmetry also has to freeze and then pick out which part of the particle will behave one way and which part of the particle will behave another way. So in our universe, we might see electron as a fermion. They have spin half, and they cannot. We have atoms. In a different universe, electrons might actually be a boson. Electrons might be a selectron. It will have spin 0, right? And in some other universe, maybe the electron will have spin 1. Who knows? Of course, the content of the universe might be terrible, right? Like there might not be galaxies or like life at all, because the way supersymmetry is, frozen out is different. Just like how different magnets have different magnetic domains, different snowflake behaves, it has a slightly different shape. Like, yeah, the supersymmetry breaking mechanism might explain how the different variations of the universes. And this is definitely something that people have tried to explore with string theory, because string theory needs supersymmetry, and that's a fact. And if string theory were to explain the world, yeah, it needs to have, there's a mechanism to create these variations.
Gotcha. So, Mikey, I know you have to leave very soon, so I want to take this opportunity to let you guys, there's some audience questions, but I want to prioritize Mikey being able to leave soon. So just in tradition, as we've been doing, any parting words from you both, and then we'll move on to the audience questions. So, Mikey, you go first.
Yeah, sure. Yeah, I don't know. I like the way that this conversation started in terms of like the conviction for believing in something like supersymmetry. And I just wanted to reiterate, like, the universe, like, so as Tim mentioned, like we have these different kinds of particles. They have different kinds of properties, spins, or whatever. And yeah, you can take the approach of like, okay, there's just two different kinds of particles. But supersymmetry represents the discovery of a mathematical structure that allows us to talk about all of these different types of particles as though they're basically the same object. And that's just got to be how nature works at a fundamental level. I guess you can call that a religion. Well, I mean, it's not like a blind religion. It's like I think one that's slightly more well informed. Most, but yeah, conviction.
But Tim, do you want to go ahead and say any parting
Oh.
words?
Oh, I thought we could continue, but that's okay. I guess Mike, you need to head out
I'm
soon
gonna
enough.
drop off. Yeah.
Okay, well, I'll see you.
Oh,
Yeah.
I guess then we can just continue, and then
Yeah.
and then we can give
Right.
your parting
Okay,
words.
see you, Mikey.
Okay. All right.
Yeah.
See you, Mikey. Yeah. So I guess Tim, where did we leave off? I think one thing is like one question I wanted to ask you is that like if you take this to its logical conclusion and everything is related to everything else, does that mean you could say like an electron through supersymmetry is actually like a graviton, the particle that represents gravity, and gravity, as we know, is space-time itself. So is an electron space-time itself through supersymmetry, or just want to understand that more?
Yeah, so not quite yet. Actually, the most basic form of supersymmetry, it just adds one extra supersymmetric dimensions. It just means that every particle will have its partner. So for example, electron will have a selectron partner. We haven't seen it yet, but it will be that particle should have properties very similar to the electron, except instead of fermion, it's a boson. Instead of spin half, it should have spin 0, right?
Okay.
And the same thing should apply to, let's say, particle of light. The photon should have a partner. We call it the photino, whatever. But let's not delve into that. But the force carrier will have a fermion partner, and the graviton will have what we call gravitino, a fermion counterpart to the graviton. But that's not quite relating everything yet, right? Because let's say you go to graviton, gravitino, you can go back and forth. That's where the superspace ends. But that's just one step of superspace. People have discovered that you can actually, once you have one, you could have more. But there's an upper bound, it turns out. You could have maximally 4. And if you have 4, every particle will be ultimately related to everything else. Basically, it means that you go to graviton, you can take one step into superspace, you can get gravitino. You can take another step, the gravitino will have a different spin. It can become like a I don't know. There's no name for that, but like graviton force number 1, I don't know. Right? But you'll be able to take multiple steps in these different directions in the superspace, and you can walk from the electron to the graviton, basically, if you have enough. Yeah.
Go ahead.
Yeah, so basically it turns out that mathematically there is an upper bound, and that's 4 or 8, depending on how you count it. And when that happens, you get, when you incorporate that, let's say the string theory, then everything is just strings, basically. They're all related.
I see. So how do you? I mean, that's pretty wild, actually, to think that you could like go from an electron to like a particle of gravity if it does exist. But I think most people would agree that like it probably does exist, given the observation of gravity waves and whatnot. But how do you explain like conservation of charge? Like gravity doesn't have any charge, as far as I know. An electron has a charge of like -1 or +1, depending on your convention. And so how do you explain this discrepancy between like conservation of charge, for instance?
Yeah, the conservation of charge is totally fine. If you believe this grand unification, then the fact that we have electric charge is just a remnant of something greater. Then electric charge must be part of some greater force structure. There might be many, many different types of charges. And in the early universe, these charges can just spontaneously come and go. And we have examples of that in particle physics. It's like the strong force. Like we never talk about the color of a quark because it's so readily, it can just obtain a color and shed a color. Just like imagine And it's similar like in the early universe. If you're an electron just swimming, if you're an electron kind of just swimming around in this plasma, you can easily just kind of pair up with another positron or not. So the fact that you have a charge doesn't it's not a big deal anymore. You can easily shed it, obtain it. You know, your surrounding kind of just averages out. So charges becomes not a thing. You know, the reason we see charges because is a distinction between things that have charge versus things that don't. There's a distinction. But the reason there's a distinction is because our universe is cold. You know, it has picked up a particular type of relationship and called that a charge, basically. But if the universe didn't have that, you know, charges wouldn't be as big of a deal, basically.
I see. So what you're saying in all of this, what I gathered is that charge is part of this like grander structure. If you think of charges, if you think of ground unification, and so charge doesn't ultimately matter.
Yeah.
And then
like,
just to clarify for the audience, oh, go ahead. Sorry.
Yeah, I guess a good analogy is like currency, right? Like if you have one Chinese yen versus one US dollar, of course your preference is well, I want one US dollar. It's worth more.
Yeah.
But maybe if you imagine a perfectly equal world, like it wouldn't matter if you have one US dollar versus, you know, a Chinese yen, right? I mean, you can have even some dollar. I don't know, like what is it, like Zimbabwe dollar, like one, you know, because it's hyperinflation. Maybe $1 is worth zero, right? Like it's like having no dollar. So like one US dollar is way better than having like one Zimbabwean dollar, right? So, but we're kind of in this world now, you know, like the only charge that matters is the electric charge. So it didn't even matter if a particle has like isospin charge, whatever. It didn't matter because you can't use it for anything. But in a perfectly symmetric equal world, well, all the particles have all types of properties and they are equally prominent.
Gotcha. That makes sense. So I want to jump to I don't know what would be better if we should jump to audience questions or if you want to say your parting words and then we jump to audience questions. What would you prefer?
Probably the audience question is a little technical, so we can save it after the parting words. Yeah.
Okay, go for it. Any words of wisdom you've learned from Supersymmetry?
Yeah, I would say that I mean we haven't told the entire story of supersymmetry yet, but I would say a lot of you know, articles online or videos I've seen on supersymmetry, they are too basic. They just cover the brute facts on what supersymmetry is, but they didn't cover the insight. And of course, to a lot of people, it might seem crazy that every particle has a partner. Well, we don't see that. That's crazy. But we have to remember that it's a similar scenario when Einstein first discovered his theory of relativity. You know, he thinks that, oh, space-time is a fabric. Well, no one's seeing the fabric. He has equations that are like 4 pages long. Well, back in the days, people thought it was crazy, right? There's just so many equations. Why? You know, Newton's equation is just a few lines at best. But after a while, of course, for one thing, experimental confirmation has confirmed Einstein's theory. And his equations were simplified to one line because we have this understanding that the equations is not what matter. The complication of having fabric of spacetime is not what matter. The matter is the beautiful geometric object that Einstein described our world. You know, it's a spacetime is like an object that we live in. It's dynamic, right? And I think we're in a similar situation here with supersymmetry. You know, at its surface, you can say, oh, it's so many complicated equations. Every particle has a partner. And, you know, maybe in our lifetime, we'll never get experimental confirmation one way or another. But deep within the theory that people don't talk about is there's a beautiful structure. It's almost like Einstein's dream version 2. There's this idea of a superspace. That space-time got bigger. It got more intricate, you know. And remember that when we say there's a distinction between particles and space-time, of course, in real world, it's a big difference, right? Like my hand moves through space-time, and my hand is made of particles. They are two different statements. But remember, graviton is a particle, and space-time is basically made of graviton. Graviton is space-time itself. So we already know that particle is space-time. They're not different. So it only stand to reason that if we believe, and I truly do believe so, that there's a grand structure in the universe, then it means that all the particles in space-time is one and the same. And it's just so happened that if you buy this idea, you have this beautiful structure of the super space. It really is Einstein's dream version 2. So with that, I think, that's something that people miss when they talk about supersymmetry, because they don't understand it well enough yet to see what its promises are. And that's the problem. And sometimes you gotta, you gotta dig a little deeper to kind of be able to judge what the theory is doing.
Yeah, absolutely. Great points there. So let's move to the audience questions. So one of the questions is, can quantum particles represent collective excitations of supersymmetric partners?
Yeah, I'm not exactly sure what this question is trying to get at. So supersymmetric partners is just a term that links different particles together, and particles are quantum mechanical by their nature. But maybe the word is the collective excitation, right? So usually collective excitation refers to a material where you have a lot of stuff. And when the stuff undulates, you have what we call collective excitation. It's like I don't just have one particle, I have multiple particles move in and out, right?
Mm-hmm.
For sure, you can study toy models where you can mock up supersymmetry in material science, for example. But that's not exactly the same as thinking about it in a fundamental physics way. I would say in fundamental physics, we don't think about collective excitation because these are fundamental excitations. They just are what they are. So, I would say that, the idea of supersymmetry is to go beyond particles. Instead of thinking of one particle as one object, we're grouping different particles together into a super object, right? We're elevating it because they're all related.
Gotcha. The second question is, can we step in superspace? Can the step in superspace be the RG flow? I assume RG refers to renormalization group.
Yeah, I think this is a technical point. The answer is no, because superspace is a construct itself. It's axiomatic. It's basically a postulate to say that this is an object that exists, and the universe operates around it because the universe is a superspace. Renormalization flow is a different concept, and I don't think the two are related, at least not naively. There might be some really weird, for example, you can maybe connect the two. I don't think so. So the two concepts, let's just say that they're different.
All right. Well, that's all our audience questions. And so on that note, I want to thank everybody for joining us, and we'll see you all next week.
Yeah.